Okay, now we'll see the indeterminate trusses. Analysis of indeterminate trusses. Stiffness matrix method. First, let us see the concepts. Stiffness matrix K at a truss joint is given by, unlike the beams and frames, this stiffness matrix for a truss joint is a fixed quantity. It's like this: K11 summation of AE by L cos square theta, K12 or K21 or K22 will write first, K22 summation of AE by L sin square theta, K12 K21 summation of AE by L cos theta into sin theta. So, it's a 2 by 2 matrix is fixed quantity. To use this one, these are the conditions. Coordinates 1 and 2, coordinates 1 and 2 must be taken along positive x and positive y axis only. Then theta must be measured from positive x axis and in anti-clockwise direction only. It should be positive x axis, anti-clockwise direction. Coordinate 1 and 2 must be along positive x, positive y axis only. Rotation coordinates we will not take it because trusses they don't rotate, because any type of rotation, deformation, rotation after deformation means buckling. Rigid body rotation we don't take it because it is not unknown. So only axial displacements or axial deformations are the independent displacements. So only for them you have to give the coordinates. What it means is how to get AE by L cos square theta sin square theta is like this. So for this explanation is like this. In a big truss, we take one member, let us say. This is x axis, this is a y axis, and this is the member AB. There are many other members also are there, because in a truss only one member won't be there. One member this way, one member this way, 4-5 members also can be there. Schematically I have shown only one member AB. Let us say. Now positive x axis, it has only two displacements. It can move horizontally, it can move vertically. So the two coordinates 1 and 2 must be taken along positive x, positive y axis. So this must be your coordinate 1. This must be coordinate 2. And theta must be measured in anti-clockwise direction only, like this. This is theta. Theta AB, let us say, or theta. Why like that is, it is the Cartesian coordinate system is like this: positive x axis, positive y axis. From x axis to y axis if you rotate, that is positive rotation. When you are rotating from positive x axis to positive y axis like this, whatever direction the nut advances, that is a positive direction, positive z axis direction. rotate like this, z axis will go this way. So this is positive z axis. X, Y, Z, positive rotation. So that system if you follow, this is the formula you can use. Now you see how to get that AE by L cos square theta. So K11 means like this. Force at coordinate 1 to produce unit displacement at coordinate 1. That means this is the joint, it has to move somewhere here, say. This one, let us say delta 1 is equal to 1. If it moves here, then how much force is developed? We have to fix this one, only this moved like this. Now you see how to get that value is like this. This is what you have studied. In any member, delta is equal to, deformation of the member is equal to PL by AE. That means P is equal to AE by L into delta. If delta becomes 1, then P becomes AE by L. Force P required is AE by L for unit displacement. Now you see, if this is 1, I drop a perpendicular line here, or say here, to like this. Okay, because this is the displacement. This displacement has x component, y component. I wanted this to be 1, that's all. So that one displacement I split into two components. If this is theta, what is this length? 1 cos theta. This is from here to here 1 sin theta. This displacement is sin theta. Okay. So axially it is moving by a distance of, if it is moving like this means axial deformation is 1 cos theta. For 1 we know AE by L. For 1 cos theta how much force I have to apply here? I am pushing it. This displacement is 1 cos theta. How much force I have to apply so that contraction is cos theta? For contraction 1, force required is AE by L. For cos theta, this value is AE by L into cos theta. But I don't want force in this direction. I want its x component. What is this x component here in this direction? X component of this is AE by L cos theta into cos theta. I will get x component. So K11 is AE by L cos theta in this direction, whose x component is this one. So AE by L cos square theta. So like that. For one member AE by L cos square theta. If at all 2-3 members are there, so all such AE by L cos square theta terms you have to add. Then you will know what is the total force required to move horizontally by 1. This is for one member. If 3-4 members are there, I have to hold them, push them. So sum I have to take it. That's why I have taken summation. Here summation means all such member summation of AE by L cos square theta of each member. If 4 members are there, AE by L cos square theta for AB, AC, AD, like that. All members you have to sum them. Then similarly K22 means force required to produce unit displacement. In the here I put delta 1 is equal to 1, close, remove it off. Put the same thing here, delta 2 is equal to 1. If I put 1, then this component will become cos theta, this becomes sin theta component. So this force required is AE by L sin theta. Then because this is 1, this becomes, here it is cos theta, now this becomes theta. So AE by L sin theta into sin theta, you will get the y component, y direction force. This force I am trying to find now y component. So AE by L sin theta into sin theta, I will get the y component of this one. So AE by L sin square theta. Similarly 1 2 and 2 1, same way you can find. So from the simple geometry, trigonometrical conditions, I can get these three values. The derivation of that actually not required in the exam because you have only 30 seconds time, so you must remember. At least you must know why that sigma stands for, what that sigma stands for, how AE by L cos square theta comes. If you know that this and this, automatically we can remember because you know the logic behind it. Otherwise, simply by hearting means the cos square theta will become after some time cos theta. Then there is no way you will get the correct one. But if you know how to get that value, that means you understood that value, then remember, it will be remembered for longer periods of time. Okay. So like this we get them, and this is the how we have to measure the theta. Next, having found stiffness matrix, they will ask you only one element or a 2 by 2 mat. 2 by 2 matrix till now they didn't ask you because it will take 3 to 4 minutes time. Any one element they give you. K11 they have asked till now around 5 to 6 times. In a different wording, K11 they have asked. Okay. Now assume that you have formed a 2 by 2 matrix and invert it and find the displacements. Aim of the stiffness matrix analysis is finding the unknown displacements I told you. After finding the displacements, you have to find the forces in the members. So, you cannot find the displacements. Even two displacements also you cannot find in 2 minutes time. Two displacements if you want to find, it will take minimum 7 to 8 minutes time. So, that is for 20 marks questions. So, finding the displacements is the beyond the scope. So, they will give you the displacements. If you know the displacements of joint A, joint B, what is the force in the member? 1 minute you can complete. Because we know the displacements say, then how much member elongated or contracted we know from the trigonometry. Then find the force. So that is your second point. This also I remove. Second point is force in any member AB is given by FAB is equal to minus AE by L, difference of x displacements, delta AX minus delta BX into cos theta AB plus difference of y displacements, delta AY minus delta BY into sin theta AB. This is how you have to find, where delta AX, delta AY are x and y displacements of joint A. Next, delta Bx, delta By, x and y displacements of joint B. Theta AB, this is angle of inclination of member AB measured from positive x-axis and in the anti-clockwise direction only. As I have told you, from the positive x-axis theta must be measured. Okay. Then here what it means is how to get this one. Here I will explain. Okay. Now, if you take same earlier diagram, x-axis, y-axis. This is the member AB. AB. After the joints are displaced, A will come to somewhere here, say, has come to A dash. B has come to somewhere here. That rotations, when compared with theta, change in theta is very less. So, that change in theta we will neglect, theta only we take it. So, AB has now become A dash B dash. There is a small change in the rotation also, but I told you we have solved that rotation of the member AB is 0.001 radian. Like that you got it. Compared to 30 degrees, 0.001 degree means you can neglect it. Like that. So, A dash B dash is the final position. This angle, let us say theta AB, measured in the anticlockwise direction. This displacement, A has come to A dash, because in a truss, big truss, one member, when after loading it will move. First joint will move, second joint also will move. So, that position is like this, say. This displacement is displacement of A in x direction. Here to here, this is displacement of A in y direction. Again, same thing here. This is displacement of B in y direction. From here to here, this is displacement of B in x direction. Now, how much the blue color line elongated or how much blue color line contracted? That is the axial deformation. If I know two displacements here, I can know whether it elongated or contracted. How? Only x displacements you take it. It has moved from here to here, delta Ax. What is the displacement component in this direction? If I take delta Ax cos theta, I will get how much it moved. Cos theta means this component I will get. So, delta Ax cos theta, let us say 3 mm. Similarly, delta Bx cos theta, let us say 5 mm. That means what is the net elongation? This is 3 mm here, 3 mm moved up, 5 mm moved up. That means as a rigid body it moved by 3 mm, another 2 mm here extra. That means only 2 mm is the actual elongation. Now you see here, delta Ax into cos theta 3 mm, delta Bx into cos theta 5 mm. So 3 minus 5 minus 2 mm, minus 2 mm into already minus 2 was there, so plus 2 mm. That means there is an elongation. If you get this quantity plus, that means FAB is tensile. Okay. So, delta Ax minus delta Bx cos theta is the x deformation. Similarly, delta Ay sin theta, delta Ay into sin theta is the component of delta Ay in this direction. Delta Ay sin theta in this direction, let us say 1 mm. Delta By sin theta, let us say 6 mm. So, 6 mm minus 1 mm, 5 mm only is the net elongation. Now, you see, delta Ay sin theta minus delta By sin theta is 5 mm. So, minus 5 mm you will get, minus into minus plus. That means if this quantity is plus, it means tensile. So, from here to here, this is actually, it is the net deformation. Difference of x displacements into cos, y displacements into sin, you will know the net deformation because of the xy displacements. This is net deformation. Net deformation delta. If delta is negative, then negative into negative it becomes plus, then tensile. If delta is negative, it means that it is elongation. If delta is positive, it is contraction. As per that sign convention, positive means contraction, negative means elongation. Now, negative means elongation, negative into already minus I have written. If you don't want to deal this, we put plus, let us say, then change this one. Plus AE by L, BX minus AX if you write, then you will get positive means elongation. Negative means contraction, directly you can get it, but we have taken minus out. So AB, first letter deformation AB means first minus second one. First to second, like that when you go, you have to write minus. Okay. Now, accordingly, if net deformation delta is negative means negative minus negative, negative into negative plus. So, if FAB is positive, comma, then it means that it is a tensile force. If FAB is negative, then it means that it is a compressive force. It is a compressive force. Now, these 2 points only we have to remember in the exam. Either they will ask you stiffness, one stiffness coefficient, or they give you the displacements AX, BX, AY, BY, they will give you. You have to find FAB by substituting in this one. Or if you have to find the displacement also, let us say, only one displacement you can find in 2 minutes time. So, these are the 3 possible ways of asking the questions. Let us see how they ask those questions. Now, it says stiffness coefficient K11 is they give you a structure like this. This is one length L, AE is the stiffness. This point, let us say A, B, 45 degrees. This is the question. One element they have given is one structure, you can take it. You see, this member AB is not loaded at intermediate location, connected by pins, so it is a link. Link means axially loaded member, means it is a truss element. Truss element K11 means what you have to write? See, coordinate 1 they have given. Supposing that if they don't give like this, let us see what is dk for this one. How the questions can be asked is dk. What is the kinematic indeterminacy here? You see, here rotations you should not count in a truss. So here dk is 0. XY translation is also not possible because it is a hinge. Rotations we should not count because it means it is a buckling. At A, y direction it cannot move, only x direction. So dk is 1 here. So dk is only 1, delta Ax. Okay. So what is the size of the stiffness matrix? So size or order of stiffness matrix is, I told you, dk by dk. It is a 1 by 1 matrix. So 2 marks you will get for this one. If they ask you a question, what is the size of stiffness matrix? If they ask, simply 1 by 1. Okay. Now let us see, this is a 2 marks question. Let us come to actual solution. So since the size is 1, stiffness matrix K, you have only one element in this one, K11, summation of AE by L cos square theta. How many members are there at A? Only one, so summation not required. AE by L, so theta AB. I told you theta must be measured from positive x-axis to the member. 45 degrees you should not take it. From here you have to measure like this. So 90 plus 45. So theta AB you have to take it as 135 degrees, not 45. So for the member theta AB 135 degrees, not 45 degrees. Measured from positive x-axis. Maybe result is same, but you have to measure like this only. So AE by L is given. So K11, only one member, AE by L cos square 135 degrees, means 45 means 1 by root 2 square. So AE by 2L. So in one paper they asked 5 to 6 times they have asked this one, what is K11? It is AE by 2L. In another paper what they asked is, what is the axial stiffness of or K11 in its longitudinal direction? Then no cos theta will be there, simply AE by L. Stiffness of the member in its longitudinal direction means local coordinate, or simply in the actual member coordinate. If you take it AE by L itself, that you can take it. See here, if you have a member like this, say AB, coordinate 1, I give it like this, say. What is K11? Simply AE by L, because theta is 180 degrees. So AE by L it will become. In one paper they asked this way. If coordinate 1 is like this. Now in this case member is this way, coordinate 1 is this way. Then you have to take theta 135 degrees. Clear? So this is one paper, this is another paper, another paper. This one they asked 4 to 5 times. In one of the IES paper they asked this one. A member axial stiffness in the direction of the, in the longitudinal direction is AE by L. Now let us see one more member. This is one way. Another way is they give you the displacements, you have to find the force. Member AB of a pin jointed truss lying in xy plane has coordinates a 0 0 means origin, b 3 root 3 comma 3 meters. Coordinates of AB when they give, it means that you are asked to find the angle of inclination of the member AB. Joints A and B are displaced. Why joints A and B are displaced? Once you load them, truss joints they move, they rotate also. Means members will rotate as rigid body. That they are giving. Joints A and B are displaced and X and Y components. X and Y components are, they give you like this: UA, VA, UB, VB. This is another way of telling, mentioning the coordinates. In your fluid mechanics, um, the displacement of water positions means U, V, W. X displacement is U, Y displacement is V, Z direction displacement is W. The velocity potentials also you have seen that U, V, W they mention. So that coordinates they have given. U, V like that is 1 root 3, 2 root 3 mm. These 4 displacements they have to give us. We cannot find in 2 minutes time. It will take half an hour to 45 minutes time if you have to find these displacements. Because you have to develop a 4x4 matrix minimum and invert it. No way we can complete without the help of computers. So they give you the displacements. For this bar, AE by L also they have to give us axial stiffness. AE by L is equal to 100 kilonewtons per mm. This they have given. Force induced in the bar, how much is induced or developed? Force induced in the bar by the end displacements is, because of the displacements of the joints, force will be developed in the member. It will elongate or contract. So, based on the description, first you see this A, B they have given, that means this one, x-axis, y-axis. This is the member AB. AB. Coordinates of A is 0, 0. Coordinate of B is 3 root 3, 3 meters. That means what? This length is 3 root 3 meters. This is 3 meters. With this information, I can find theta AB. What is theta AB? Tan theta AB is equal to 3 by 3 root 3. That means 1 by root 3. So you will get theta AB is equal to 1 by root 3 means 30 degrees. So angle of inclination of the member with respect to coordinates they have given. So this must be coordinate 1. We have to choose along positive x, positive y axis only. Then what else they have given? Displacements. Delta A, as per, actually he has given UA. In our notation it is displacement of A in x direction is 1 mm. Then VA, in our notation delta AY is root 3 mm. Next UB, for us delta B in x direction 2 mm. VB means delta B y direction 2 root 3 mm. See, all information is known to us. Now force in the member AB is minus AE by L, difference of x displacements delta AX minus delta BX cos theta AB plus difference of y displacements delta AY minus delta BY into sin theta AB. Now minus AE by L has given minus 100, delta AX 1 mm minus delta BX 2 mm cos 30 degrees plus delta AY root 3 BY 2 root 3 sin 30. We know how to manage this one. This is minus 1 cos 30 minus root 3 sin 30. So result is minus root 3. So minus 100 into, I will write here, FAB is equal to minus 100 into minus root 3. So plus 173.2 kilonewton tensile. Positive sign indicates that FAB is a tensile force, like that. So in 2 minutes time, what he has given, what we have to find. In this expression, direct substitution only we can make it. They have to give us the displacements, they have to give theta. Instead of giving directly theta, coordinates of the members, the ends they have given, so that you can find theta. Substitute. Okay. Next, another way of asking is like this. Now you can also find the displacements. Means you can take the matrix inversion, means not possible 2 by 2 and find 2 displacements because of the time. Let us see how they can ask you that problem. For the truss shown in figure, horizontal displacement of the joint A is instead of giving one member, now they have given two members, like this. Okay, this point let us say A, B, C. This angle of inclination 45 degrees. Then AE by L, axial stiffness is Z, let us take it, constant for all members. Axial stiffness put together is constant for all members. Okay, he is asking what is the horizontal displacement of joint A when a load P is applied. Okay, this is the problem. You have 2 minutes time for this one. Just let us observe what is dk. At B, dk is 0. At C, dk is 0. At A, dk is 1. What is that 1? Y direction it cannot move. In the exam, if at all they give you indeterminate trusses, they have to give us the indeterminate truss whose kinematic indeterminacy must be 1. Static indeterminacy can be anything, but kinematic indeterminacy must be 1. Then only one equation you have to solve it, otherwise beyond the scope. So note dk is equal to 1 delta Ax. So size of stiffness matrix K is 1 by 1. They can ask you up to this itself as a 2 marks question. What is the size of stiffness matrix? dk by dk. Next, let us see how to find the stiffness matrix. Your solution. First thing is, what is the stiffness matrix? K. You have only one element, K11. Because size is 1 means only one element will be there. Summation of AE by L cos square theta. Now summation is required because at A there are two members. So I have to write AE by L cos square theta for the member AC plus AE by L cos square theta for the member AB. AB and AC you have to calculate. So theta AC, how much you have to take? Then because dk is 1, you have no choice other than taking this as coordinate 1. You cannot take coordinate 2 because displacement is impossible. Y direction it cannot move. If displacement is impossible and still if you take coordinate in that direction, it means that stiffness matrix will not exist. So one has to be like this only. And your theta you have to measure like this. Theta AC means from here to here you have to measure. You should not write 0 degrees. So this is theta AC. This is x-axis. Member is like this. So theta AC is 180 degrees. Theta AB from here to here. This is your theta AB. 135 degrees. So theta AC is 180 degrees. Theta AB is 135 degrees. So AE by L is Z for both the members. So K11 is Z cos square 180 degrees plus Z cos square 135 degrees. 180 means 1, 135 means 1 by root 2, that means 1 by 2. So K11 you will get Z plus 0.5 Z, 1.5 Z. So your K is only one element, K11, 1.5 Z. How to read that K? So we will read now this K. K is nothing but only one element, 1.5 Z. What is this one? Force required at 1 to produce unit displacement at 1. That is the meaning. That means for 1.5 Z force, displacement of A in x direction is 1. For P force, delta AX how much? This is a 2 biscuits 5 rupees. 5 biscuits how much? Like that. So delta AX will be naturally, for this is 1, for this much force how much? So P by 1.5 Z, or we can say P by K matrix, P by 1.5 Z, we can take it. So P by this much is enough. If at all they give AE by L is equal to K, they give say P by 1.5 into K we have to write, because AE by L, if they ask it as K, to differentiate it between this K and that K, I have written it as Z. Okay, so P by 1.5 Z or P by 1.5 K, if at all AE by L value is K. So like this, only 1 minute you can complete. First you have to find K11 stiffness matrix. Then stiffness matrix meaning is the force for unit displacement. For K force, displacement is 1. For P force, how much? It's like that. K force displacement is 1. P force, how much? P by K. That's all. P by that K is 1.5 Z. Only to this extent they can ask you in the exam. A 2 by 2 matrix developing is impossible. Now, let us see one more problem. In a redundant joint model, some structure it is 3 bar members are pin connected. Pin connected at Q. At Q as shown in figure. Under some load, placed at Q. How much load? Some load was there, it is placed at Q. The elongation of the members, this they have to give us. The elongation of members MQ and OQ are found to be 48 mm and 35 mm. See, they are elongations and those values are 48 and 35 mm respectively. Then the horizontal displacement U and vertical displacement V of the node Q. Node means joint. Node Q in mm will be respectively. And they have given you the truss. Like this, they have given 3-member model. This is M, N, O, Q. This he has taken X corresponding displacement U. This he has taken Y corresponding displacement U. Then also they have given Mn. Mn value is 400 mm. No is 500 mm. Then NQ 500 mm. Then 4 options are like this: minus 6.64 and 56.14, 6.64 and 56.14, 0 and 59.41, 59.41 and 0. Like this they have asked. First you see it is a statically indeterminate structure. It's a statically indeterminate but kinematically indeterminate too. See here, this x, y displacements, 2 displacements are there. But still we cannot analyze that they have to give us the result. He has given the final displacements also. Final displacements means load member elongations they have given. Because of those elongations, how much joint Q might have moved down, might have moved horizontal. How much, what are the XY displacements? That's all. That means force he has given, angles they have given, final elongations they have given. You only have to find XY displacements. Okay, delta AX, delta AY, two displacements you have to find. But this way, XY coordinates, if I take it, we don't know how to manage. So we turned this problem into our problem. This is how we will manage. See here, this is our actual thing. Okay, like this he has given. This distance MN is 500 mm. MNO. This he has given 500. NO, MN is 400. 400. This is 500. This is also 500. Okay. Now, as far as our coordinate system is concerned, positive, this can move horizontally, vertically, positive x-axis, and this is your x-axis for us, this is y-axis. Accordingly, this is your coordinate 1, coordinate 2. Like this we have to take. First we solve as per our known problem, then we will see what accordingly we can say. If I get our displacement in y direction, you get say plus 5 mm, but he has given y downward, that means you will write it as minus 5 mm, because opposite to y axis it is acting. So that will not be an issue at all. This point is say Q. Okay, this is our problem. Okay, now let us see this angle we can find. See here, if this is 500, this is 500, this angle is theta QO, 45 degrees. Theta QN is 90 degrees, that we can find. Theta QO, 45 degrees. Theta QN, 90 degrees. Theta QM, we have to find. For that, first you calculate this angle, say alpha. Tan alpha is equal to 400 by 500. So from this alpha you will get 38.65 degrees. So if this is 38.65, then what is theta QM? You have to measure from positive x-axis. From here to here, this is theta QM, 90 plus 38.65. So you will get 128.65. Okay. Now he has given force, the elongations directly. Now we don't know how to manage with elongations. We know only how to manage with forces. Let us see what we know. We will substitute. Force, elongation in the member Mn. He has given force in the member MQ. He has given MQ elongation, OQ elongation. That elongations where in our expressions come, there you substitute. Direct substitution only. So force in the member MQ, it will, you can see force in the member MQ is minus AE by L into difference of x displacements, delta mx minus delta qx cos theta mq, plus difference of y displacements, delta my minus delta qy into sin theta mq. This total value he has given. This is net deformation. He has given elongation delta mq. He has given 35, mq is minus 48 mm. You have to write minus 40 mm because negative because elongation. Okay. Now delta mx. How much m will move in x direction? Delta mx is equal to delta my. Both of them are 0 because hinge support. Mx, my 0. Qx, qy only unknown. Theta mq we know already. Theta qm is 128.65. So this we will write it from this one. This we are not interested. Net deformation he has given. Delta mx is 0 minus delta qx you have to find into cos theta mq, qm 128.65 plus delta my is 0 minus qy. We have to find delta qy into sine 128.65 degrees. Its value must be minus 48. Minus you have to write because it is elongation. So you will get finally all minuses if you cancel. Delta qx cos 128.65 plus delta qy sine 128.65 is equal to 48. This you call it as equation 1. Next, pi direction. Another member also has given OQ elongation is 35 mm. Force in the member OQ, how much it is we don't know, elongation we know. That elongation means this part minus AE by L delta this delta QX here we have to write when you are taking Q as the joint, let us say this must be first Q should be there. This is delta QX minus delta MX. Here also first one is must be Q because from Q only we have started. Our coordinate we have taken at Q. So delta QY minus delta MY. So you will get this is plus because this is delta QX minus 0. This is delta QY minus 0 is minus 48 mm. So delta QX cos delta QY sin is equal to minus 48 you will get. So is the case here OQ. Q is the beginning point. So delta QX minus delta OX cos theta OQ plus delta QY difference of x displacements delta OY into sine theta OQ. Its value is minus 35 mm. So you will get one more equation. Only this part is minus 35 mm. Only this part. We will write only this part is delta OQ minus 35 mm. Not AE by L. Force is not minus 35 mm. This net deformation is minus 35 mm. Now from this one you will get delta QX theta OQ is 90 degree, OQ is 45 degrees. Delta QX cos 45 degrees plus delta QY sin 45 degrees is equal to minus 35. See, cos 45 means 1 by root 2, 1 by root 2. Solution becomes simpler. Solving 1 and 2, you will get delta Qx is nothing but here u displacement for him, 6.64 mm. Delta Qy, for him it is v displacement. For us you got it as delta Qy minus 56.14. This is our answer, u and v. See, y direction as per him, y axis is this one. For us y axis is upward. Here if you get y axis delta Qy negative means what? It cannot act upward, it should be downward. So downward there positive y axis. So both have to be positive in the option. So 6.64, 56.14 you have to answer, because for him y axis is downward, for us y axis is upward. For you if you get negative, it means that it cannot act upward, it has to act downward in this direction, that means plus. So B is the option. Like that. You see, in this entire problem, you only have to use either the stiffness matrix 2 by 2 matrix or what is the force in the member. Somewhere in the force in the member, that I told you net deformation quantity. That net deformation quantity, if it is negative, it means elongation. If that net deformation is positive, then it means it is contraction. So to that extent we have to be careful. Complete information, whatever I told you, you have to be thorough. Then whatever way they ask you, you will be able to solve. This is actually in one of the GATE papers given as a 2 marks question. Full 2 minutes will be exhausted if you had done before. Otherwise, first time when you want to do it, means XY, the geometry if you maintain, we will get lost in that. It will take minimum 5 to 6 minutes time to manage. But as per the formula, what is the force in the member, that means it is a matrix method, displacements they have given, that means we have to take stiffness matrix method. If you get the idea, systematically we can complete the problem in time without any confusion. Okay. So after this, we will take the flexibility matrix method. Now we have learned about the stiffness matrix method fundamentals, how to develop a stiffness matrix, a 2 by 2 stiffness matrix or a single stiffness coefficient, and also stiffness matrix for a truss where dk is only 2, a 2 by 2 stiffness matrix you will get. Either you will be asked to form or to find a single coefficient, or you will be asked to find the force in the truss member, provided the 4 displacements at the 2 joints, the 4 displacements, xy displacements at each joint, they have to give us. Otherwise, we cannot manage the problems. Even in mains also, we cannot manage the problems. Okay. Then if you have to find the displacement also, then dk has to be only 1. Then that one matrix means inversion takes only 5 seconds time. As I have explained to you in one problem, it hardly takes 20 to 30 seconds time to answer that question. Let us say 1 minute, because 1 minute you give it for thinking, another 20 or 30 seconds for solving the problem. Our time slot 2 minutes means within that we can complete the problems. In the exam, the questions will be such that we should not think too much, we should not calculate too much. Questions are very, very fundamental in nature. Have we understood the basics or not? The aim of GATE or ESE Prelims exam is only that, to test your conceptual capabilities, not your calculation capabilities. Okay. So can we, did we understand the concepts better or not is the thing that will be tested. Okay. Now we will see another method called flexibility matrix method. This flexibility matrix method comes from Castigliano's theorem 2. Dou square u by dou x square, we have to take it. There in Castigliano's theorem 1, we have taken the strain energy expressed in terms of displacements. Second differentiation will give you stiffness coefficient. Only first differentiation gives you for a given displacement delta what is the force required. Okay. If you differentiate that force again with respect to the x redundant force or whatever it is, you will get the force required to produce unit displacement. Okay. Now Castigliano's theorem 2, in the same way we use it to find the flexibility coefficients. Now to get that, energy must be expressed in terms of loads. Then dou u by dou x will give you the displacement for the x force. Differentiate it again, you will get displacement due to unit force. That displacement due to unit force, we want to call it as flexibility. Okay. Accordingly, I told you Castigliano's theorem 2 will give you a set of flexibility coefficients or a set of compatibility conditions. As in the stiffness matrix method, flexibility matrix method also applicable only to linear elastic structures. If you want to apply to non-linear elastic structures, you have a Crotty-Engesar theorem. Crotty-Engesar theorem deals with the complementary energy. First derivative of complementary energy with respect to force will give you the displacement. But for linear elastic structure, complementary energy, strain energy are same. Then Crotty-Engesar theorem becomes same as Castigliano's theorem 2. So that was the theory I have discussed. Now we will take up how to get that set of compatibility conditions from the Castigliano's theorem 2. Okay. Now let us see flexibility matrix method. First one, as in the stiffness, you have the flexibility. I defined stiffness, now we are defining flexibility. Flexibility we call it as delta. It is the displacement produced due to unit force. Due to unit force. Force must be unit. How much is the displacement? We call it as flexibility. That means flexibility is nothing but the displacement produced because of unit force. Now it is the inverse of stiffness. Stiffness inverse is flexibility, or flexibility inverse is stiffness. Then I have given you types of stiffness. Similar to that, we have types of flexibility. First one is axial flexibility. Delta 1,1. This is inverse of axial stiffness. 1 by AE by L. So you will get L by AE. L by AE is called axial flexibility. Now you see, we know that how to get this is delta is equal to PL by AE. This is what strength of materials we have studied. If P becomes 1, if applied load becomes 1, delta becomes L by AE. This is called flexibility. So flexibility means displacement produced due to unit force. So since again you don't have to use Castigliano's theorem 2 to find the flexibility coefficients, because our strength of materials concepts, whatever sir told you in the deflections chapter, those things are enough to complete in the examination in our 30 seconds time period. Okay. So this is how you will get axial flexibility. Next, transverse stiffness you have taken. Now similar to that, you have transverse flexibility. This we call it as delta 2 2. This is 1 by transverse stiffness. One by this I have given you 12 EI by L cube. So you will get L cube by 12 EI. Transverse stiffness, flexibility. Then flexural stiffness you have studied. Now we have flexural flexibility. Flexural flexibility, you call it as delta 3 3. We take it as 1 by flexural stiffness. 1 by 4 EI by L, flexural stiffness. Now you will get L by 4 EI. Then you have torsional flexibility. In the exam, in strength of materials also, if at all they give you say flexural flexibility, that means they have given you L by 4 EI value. If R and D is hinged, they have given you L by 3 EI value and other quantities you have to calculate. First we must know how the flexural flexibility looks like. Which quantity is called flexural flexibility. Then in the SM problems also you can complete the questions. In the theory of simple bending, you can solve the problems fast. Next, torsional flexibility. Delta 4 4. Then we can write it as 1 by torsional stiffness. 1 by Cj by L. So L by Cj we call it as torsional flexibility. Cj is torsional rigidity. Cj by L is torsional stiffness. Inverse of that, that means L by Cj we call it as torsional flexibility. So similar to types of stiffness, you have types of flexibility. Next, after this we have taken the characteristics of the stiffness matrix. Now we will see characteristics of the flexibility matrix. Third concept, characteristics of flexibility matrix. Delta. Now here also, to get the first column of flexibility matrix, in this case what we do is, first in the stiffness matrix method, independent displacements are, let us say, 2. Then dk by dk is the size of the stiffness matrix, 2 by 2 is the matrix. All independent displacements, what you have done, you fix them, you restrain them. A symbolic representation of fixing all the displacements. Then one by one you remove them and find what is the force required to produce the unit displacement you have calculated. So Castiglione's theorem 1, 2 times if you differentiate strain energy, you will get the stiffness coefficients. Now you will calculate ds, static indeterminacy. Static indeterminacy, let us say 2. That means 2 unknown reactions you cannot find using equations of equilibrium. So your strain energy must be expressed in terms of those unknown reactions. So that means in terms of forces you have to write the strain energy. Then 2 times when you differentiate the strain energy, dou u by dou x 1, then you will give you the displacement. You will get the displacement. Then again you differentiate it, you will get the unit displacement. That means if the force becomes unit, what is the displacement you will get? Dou square u by dou x1 square. You will get force displacement produced due to unit force you will get. Okay. So supposing that ds is 2, then remove the redundants, make it as a statically determinate structure. We call it as a released structure. Wherever redundant reactions you removed, give the coordinate numbers to them. Like you have given coordinate numbers to the displacements in the stiffness matrix method. Now you will give coordinate numbers to redundant forces. After removing the redundants, give the coordinate numbers. So once you remove a redundant forces, a statically indeterminate structure becomes a determinate structure because all redundants you removed. That determinate structure we call it as a released structure. Released from whom? Released from the redundants. So on that released structure, show the coordinate numbers. If you want to get first column of the flexibility matrix, on the first coordinate apply unit force. Find the displacements. Again, Castigliano's theorem 2 not required. Strength of materials formulas are enough. One force you apply, how much is the displacement? So what are all the displacements produced or developed at all coordinates because of the unit force at coordinate 1? List out them. That is the first column. Second column means in the second coordinate apply unit force. Because of that force, what are all the displacements you are getting, you list them. That is called second column. That means your flexibility matrix gives you a displacement matrix produced because of unit force. Okay. So that is the first point, how we build the flexibility matrix. I give that where I told you. To get first column of flexibility matrix, apply unit force at coordinate 1 and find displacements at all coordinates, where at all coordinates in the released structure. Then what is that released structure? In flexibility matrix method, coordinate numbers are given to redundant forces. If we remove all the redundant forces, we get a released structure or statically determinate structure which is immovable. Which is immovable means you have removed the redundants, let us say. After removing the redundants, there must be sufficient number of reactions. That means at least minimum 3 reactions must be there, so that rigid body translation or rigid body rotation should not take place. It must be a stable structure we should get. Stable, statically determinate structure. Okay. we get a released structure or statically determinate stable structure. Stable structure which is immovable. Stable structure means immovable only. Which is immovable is enough, but stable immovable structure we take it. Okay. This is what is the process. Remove the redundants, make it a stable, statically determinate structure. Give whatever removed reactions, you give the numbers to them. Okay. Then first number, give unit force, find the displacements, first column. Second number, apply unit force, find the displacements. Strength of materials formulas are enough. Okay. Similarly, to get second column, apply unit force, at coordinate 2 and find the displacements at all coordinates. In the released structure. So this is what I told you, how to get that. If you build like this, first column, second column, again here also you will get a square symmetric matrix. Now, second point is, flexibility matrix is also a square symmetric matrix. Flexibility matrix is also a square symmetric matrix. Now, symmetric why? The displacements is strength of materials I have told you, Maxwell's reciprocal displacement theorem. Okay, so from that it must be symmetric matrix. Symmetric because of Maxwell's reciprocal displacement theorem. This is a particular case of Bette's reciprocal work theorem, or we can say symmetric because of Bette's reciprocal work theorem. Because single force only we are applying, so we can take it as Maxwell's reciprocal displacement theorem. Okay. What it means is reciprocal displacement theorem. See here, this is what you have learned. Supposing that if I write flexibility matrix delta, flexibility matrix when you are writing, the first column represents only the displacements because of the unit force at coordinate 1. So you see delta 1, delta 2, delta 3. These are all the displacements because of what? Unit force at coordinate 1. So second subscript tells you where you have kept the unit force. First subscript tells you where you found the displacement. So due to unit force at 1, delta 1, delta 2, delta 3 are the displacements. List it, that is the first column. Second column again displacements, delta 1, delta 2, delta 3. Displacements at all coordinates, but because of unit force at coordinate 2, like this. Okay. Second subscript tells you where you applied unit force. Third one again, delta 1, delta 2, delta 3. Displacements at all coordinates, but because of unit force at coordinate 3, like this. Now, this is the diagonal elements, let us say. With respect to the diagonal elements, if you fold the matrix, these elements will exactly sit on that. That is the meaning of symmetry here also. Now you see, here delta 1, 2 means displacement at 1 because of the unit force at 2. Displacement at 1 or at coordinate 1 due to unit force at coordinate 2. What is that coordinate? At the coordinate 1 means what is there? Actually there is a redundant force. You remove the redundant force, you get coordinate 1. At coordinate 2 also there was a redundant force. That force can be force or moment, whatever it is. You removed it given the number. So apply unit force at 1, find the displacement at 2. Here unit force is at 2, displacement at 1 you are finding. That value is equal to this one. This means displacement at 2, coordinate 2 due to unit force at coordinate 1. Okay. So in strength of materials you have from Maxwell, delta 1 2 is equal to delta 2 1. Again, what strength of materials you have studied? From SOM also Sir might have told you. Assume that you have a continuous beam. Okay. Like this. Reactions you are finding, let us say. Remove the redundants, give the coordinate numbers. This is now equivalent to this one. At this point you remove the redundant reaction, give coordinate 1, coordinate 2. Like this, give the coordinate numbers to the redundant reactions. This point A, B, C. This is VB, this is VC. So VB, VC forces, we remove them. These are in a statically indeterminate structure like this continuous beam. VB, VC you cannot find from the equations of equilibrium because 3 reactions only you can find. So 2 extra are there. So 2 reactions you removed them, you made it like this. What it tells you is from Maxwell, delta 1, 2. Supposing that if I take it, this is coordinate 1, coordinate 2. Let us say coordinate 1, coordinate 2. Now apply unit force at coordinate 1. This is 1, let us say. Because of that, the deflected shape, curve and straight line. What is the displacement here? Delta 2. Displacement at 2. Because of what? Unit force at 1. Delta 2, 1. This value is equal to this one. I interchange the forces. Now this is coordinate 1, this is coordinate 2. Replace, you keep the unit force here. That one is unit force, blue color one is unit force here also. Due to 1 you find the displacement here. Then it is like a curve. This way it will deflect. This displacement at 1, you are finding displacement at 1, but where is the unit force? Here. SM you have studied such problems. So apply a point load at the free end. Find the deflection at the center. If they ask you, what you have done? Keep the load at center, find the deflection at end. Then both are same from Maxwell. If you remember vaguely, such examples are told you. So that one, this is this one. So from Maxwell, delta 2, 1 is equal to delta 1, 2. For them to be equal, it must be linear elastic structure only. Otherwise, they will not be equal. Okay. If you have say non-linear structure, then not this theorem, Crotty-Engelser theorem you have to take it. For that you have to take not strain energy, you must take complementary strain energy. Okay, some other coefficients you will get. Okay. Okay, now you understood the nature of the flexibility matrix. It is a square symmetric matrix. All the diagonal elements here also, they must be positive quantities and also non-zero quantities. That we take it as third point, third characteristic. Third characteristic is, in flexibility matrix, all diagonal elements are always positive and non-zero quantities. They must be positive and non-zero quantities. Why like this? From this what you have studied. From Castigliano's theorem 2, delta is equal to dou u by some dou w. First derivative of strain energy, not complementary energy. If we take first derivative of complementary energy with respect to load at any point, you will get the displacement for a non-linear elastic structure or linear elastic structure as per Crotty-Engelser theorem. If it is a linear elastic structure, complementary energy can be replaced by strain energy. If you replace it by strain energy like this, instead of u star, you can write u only for linear elastic structure, then that is equal to Castigliano's theorem 2. So delta is equal to dou u by dou w. What it tells you is, that is, first partial derivative of total strain energy with respect to load at any point in a structure gives displacement at that point in the direction of the load only. See, in the direction of load only. So this Castigliano's theorem 2 gives flexibility coefficients. How the flexibility coefficients are given? Explanation. To use Castigliano's theorem 2, energy must be expressed in terms of loads only. to use theorem 2, strain energy must be expressed in terms of loads. That means actually it is a complementary energy, and complementary energy and strain energy are equal for the case of linear elastic structure. So, complementary energy must be expressed in terms of loads. Because it is equal to strain energy, we are finding the strain energy in terms of loads. Okay. So, that is why I have given you U is equal to, in the chapter trusses, when we are dealing, I have given you entire story of strain energy, gradually applied load, suddenly applied load, impact load, and related theorems on the strain energy, etc. So much story we have given. So U is equal to, we have derived this also for one member, P square L by 2AE for axially loaded member. If you differentiate it once, what you will get? Displacement, say delta 1. You will get dou square U. This, let us say, instead of P, I will call it as X. X square L by 2AE. Force in the member, let us say X. Then not only X will be there, X1, X2, X3, so many redundant forces. Each force X square L by 2AE, X1 square L by 2AE, X2 square L by 2AE, like that, all in terms of redundant forces, you will write the energies. So, dou square U by dou X, let us say. What you will get? If you differentiate it, X square means 2X into L by 2AE. So, you will get X into L by AE. So, what is XL by AE? Is the deflection due to how much force? Due to X force. I do not want due to X force, due to unit force I want. So, differentiate this delta 1 with respect to X. So, dou delta 1, this is dou U by dou X, that is all. If I differentiate dou delta 1 by dou X, what I will get? Again differentiate it, dou square U by dou X square. Now, dou X square, when I differentiate it, L by AE. So, dou delta 1 by dou X is this one. That means dou strain energy, if you differentiate it twice with respect to X, you will get the flexibility coefficient, L by AE. This L by AE, I told you, flexibility coefficient. To be precise, this is called axial flexibility, L by AE. Dou X1, if you write it, all other things are calculated that way. Dou X1, dou X2, if you write, say, then delta 1, 2, like that, you will get. But this will tell you that by differentiating twice that energy, you will get the flexibility coefficient. That means displacement due to unit force. Only one time you differentiate the energy, say, displacement due to X force you will get. Okay, that is what we have learned in our trusses, strain energy. So, first we calculate, differentiate it with respect to some load, then you get that PKL by AU, we have got it. So, that is how it comes. Here it is only single force, single member I have given. Multiple forces, multiple members are there. Accordingly, we will write the strain energy in terms of the loads. Okay, fine. Overall, it is like this. Theorem 2 gives you displacement, again differentiate it, you will get the flexibility coefficients. That is why you have written Castigliano's theorem 2 gives flexibility coefficients. To get that flexibility coefficient, you have to write energy in terms of loads. Okay. So, this is what, now you see, delta 1 is equal to dou U by dou X. Supposing that dou delta 1 by dou X, this is K11. These quantities, L by AE quantities, I told you, delta 1 1, delta 2 2, delta 3 3, they must be non-zero quantities. That means, supposing that delta 1 1 is 0, that means what? Delta 1 is 0, let us say. With 0 force, if delta 1 displacement happened, you have a structure, you do not apply any load, that means force is 0, and apply the force is 0 at one point, let us say. If still displacement is there, that means what? It is a mechanism or unstable structure. Now delta 1 1 is 0 means what? Displacement at coordinate 1 due to unit force. If it is 0 means it is unstable structure. That means without the 0 force, why the displacement will happen? If it is happening, that means that it is unstable structure. So that's why these coefficients have to be non-zero quantities. Okay, otherwise just like that displacement will not happen. Without you applying force, if displacement happens, it means that it is unstable structure. Here also that will tell you in that way. Okay, now so now these 3 points we have to remember. That means for the stable structures only, you can find the flexibility coefficients or stiffness coefficients. Now let us see how the questions will come. You will have to find one flexibility coefficient or a 2 by 2 flexibility matrix. If at all you have to find redundant forces also, let us say, all the quantities they will give you, only one line you may have to do that inversion of the matrix and finish off in 30 or 1 minute time. Okay. Now let us see how the questions come on the flexibility matrix method. Find flexibility matrix delta with respect to coordinate system shown in figure. Once it is given as a 2 marks question, this is coordinate 1, coordinate 2. Now to save our time, he removed the redundants. He gave the coordinate numbers to the redundant forces and gave a structure like this. So, but that means what is the actual structure? One coordinate number is given to the reaction. One coordinate number is given to the moment reaction. So, the actual structure is like this. Question they have given, but we should understand that what the actual structure might be. So, this is the point. The actual structure is like this. is a fixed beam. Let us say A, B. This is the A, B. How many reactions are possible for vertical loading? VA, MA, VB, MB. HB is 0, HA is also 0. For vertical loading, loading is not given, but he didn't give coordinate number also, means that it must be vertical loading only. Okay, some vertical loading, those reactions are 0. What is the static indeterminacy for this structure? ds is equal to r minus s. 4 minus 2 is equal to 2 degrees. Okay, what is r? 4 means VA, MA, VB, MB. This I have given you earlier. Equations of equilibrium available are only two now, sigma y0, sigma m0. Sigma x0 is exhausted and also HA, HB became 0. In this case, sigma x is equal to 0 and HA and HB is equal to 0 it became, and so he didn't give the coordinate number 3 because it is 0 only. But we will take more general case also. If HB inclined loading also is there, let us say, then HHB won't be 0. Then one coordinate number must be given to horizontal reaction also. Then you will get a 3 by 3 matrix. That 3 by 3 matrix also we will develop, but this is simplest possible case where they can ask you in the 2 minutes problem. Because ds is 2, that means there are two reactions which you cannot find using equations of equilibrium. So in the flexibility matrix method, remove the two redundant reactions, replace it with the respective coordinate numbers. So remove two redundant forces. VB and MB. Give coordinate numbers 1 and 2 for VB and MB. For VB and MB. Then the released structure. Then the released structure after removing redundants is like this. He removed VB upward force. He has given a downward coordinate, no problem. Coordinate 1 for VB, that can be upward or downward. This is our choice. MB also, either he has given clockwise coordinate 2. It can be anti-clockwise also. Whatever way we want, we can keep it. So MB has given it as 2. So coordinate 1 represents VB, coordinate 2 is for MB. So this task they have done and they have given this directly to us. Okay, after removing the redundants, they gave the numbers also to them to save our time. They have given you this one. Okay. Now let us see our problem. First problem here also. Here also, first column, how to get the first column, how to get the second column, we will write. Next problem onwards, we will skip that. Flexibility matrix. First column. To get first column, apply unit force at coordinate 1. Unit force at coordinate 1 and find the displacements and find displacements at all other coordinates. At all coordinates. At all coordinates in which structure? In the released structure. At all coordinates in the released structure. Now this is how you will get it. This point is A, B, this is coordinate 1, coordinate 2. Now what we do is, you see, actually we have to find strain energy stored due to some W. We have calculated bending strain energy. Differentiate it once, you will get the deflection due to W. Differentiate it again, you will get the deflection due to unit force. That means 2 times differentiation. That much time we cannot spend in the exam, the double differentiation of Castigliano's theorem 2, because we know from strength of materials what is the deflection. So then why the Castigliano's theorem 2 we have to use? Supposing that you have a very big structure, a multi-storied frame where there are static indeterminacies say 10. Then somewhere you apply unit force, what is the displacement means you don't know the formulas. Strength of materials formulas you cannot apply. So you have to find strain energy in terms of the loads stored in the structure, then differentiate it, dou u by dou x1. Suppose load is here, displacement at some other place say, then dou square u by dou x1 into dou x2, then delta 1 2 you will get, like that. Okay. Now that much difficulty is not there because you have only 30 seconds time maximum. So we will use like this: beam, coordinate 1, coordinate 2. Now apply unit force here. This is 1. This 1 is unit force. Due to unit force, the deflection profile we know, like this it will deflect. This one, in strength of materials you call it as YB. YB means WL cube by 3EI. Instead of calculating YB is equal to WL cube by 3EI, this is what you have calculated in SM. Now we give number to the W, that YB. So where you are finding the displacement? At coordinate 1. This we will call it as delta 1. Where you applied the unit force? Again at 1 only, delta 1 1. This actual formula is W L cube by 3EI. Now W became 1. So you will get L cube by 3EI. So if W becomes 1, you will get YB becomes delta 1 1. Like that. Now because of 1, if you drop a tangent here, slope at B, this is theta B. That's what you have taken. If this is theta B, this is also theta B. Now theta B formula what you have studied in strength of materials, WL square by 2EI. If W becomes 1, this becomes, you see, delta theta B becomes now what? Where you are finding this theta B, which coordinate this corresponds to is coordinate 2. Theta B, now we call it as displacement at second coordinate. But where is the unit force? At 1. So displacement at 2 due to unit displacement. That is nothing but what you have learnt in SM is theta B. No Castigliano's theorem 2. So delta 2 1. We will get it as that formula also we know theta B, WL square by 2EI. Make W as 1, L square by 2EI. Like that. This also here it will become L square by 2EI. This what you have learnt in strength of materials, that now YB theta B you are giving numbers to them. They are known quantities now. So delta 1 1 you read like this: displacement at coordinate 1 due to unit force at coordinate 1. This is the meaning, this is how you read it. This from strength of materials we have studied that L cube by 3EI. Next, another one you calculated is displacement at 2 because of the unit force at 1. Displacement at coordinate 2 due to unit force at 1. This is L square by 2EI. This is the first column. You see all the formulas that you may have to answer in the exam, already known formulas only. No theorem to required. Similarly, you take the second column. Second column. To get second column of flexibility matrix, apply unit force. Unit force is a general term. It can be unit load, can be unit moment. In the trusses chapter I have given you, you apply unit moment, means moment whose magnitude is 1 and has no units. Here also unit force means magnitude is 1, has no units. Simply that is 1. Okay, apply unit force at coordinate 2 and find displacements at all coordinates. What it means is, this is the actual problem for us. This is the coordinate 1, this is the coordinate 2, A, B, length is L. Now at coordinate 2, you apply unit force 1. This is unit force. Unit force means that force can be moment also. Because of this, the deflection profile we know from strength of materials. If you turn like this, it should hog. So for it to hog means it should go down only. So this displacement from here to here, in strength of materials you call it as YB. What is the formula because of the moment? ml square by 2EI. If m becomes 1, this becomes L square by 2EI. Then this becomes flexibility coefficient. Okay. That is, now this we give number. Displacement, instead of YB, now you have to give some other number to this one. Where you are finding the displacement? Displacement at coordinate 1. This is the coordinate 1. But where is the force? Here is the force. That means force is at the coordinate 2. That means displacement at 1 due to unit force at coordinate 2. Now that YB became delta 1 2. Earlier case it became delta 1 1. So YB can be delta 1 1 or delta 1 2 depending on where is the force, where is the deflection. So delta 1 2. This formula we know. ml square by 2EI. Your m is 1. So you will get L square by 2EI. Then the slope. Strength of materials, this slope you have calculated it as theta b. Now we don't want to call it as theta b, we want to give number to that theta b. If this is theta b, this alternate angle also theta b. Now this is in the direction of coordinate 2 only. So this is displacement at coordinate 2. Where is the unit force? Force is also at 2. So this theta b now became delta 2 2 in matrix methods. So this value also we know the formula ML by EI for cantilever beams. So theta B is ML by EI, what you have studied in strength of materials. If M becomes 1, flexibility coefficient. Now accordingly we will write displacement at 1 because of the unit force at 2, L square by 2EI. Displacement at 2, unit force also at 2, ML by EI. ML by EI, M became 1. So L by EI. So your flexibility matrix will become like this. This is L cube by 3EI. This is L square by 2EI. This is also L square by 2EI. This is ML by EI. Because I am assuming that you are learning it for the first time, so everything we have written, where you have to apply load, where you have taken the displacement, etc. But having understood that in the exam in 2 minutes time means this much story not required. Put 1, delta 1 1, delta 1 2, we know formulas. Put moment, delta 1 1, delta here delta 1 2, delta 2 2, we can find. So formulas quickly you apply. After understanding only, thorough understanding only, the question of speed will be there. First task is you should understand how the matrix is developed. Next equal important step is the speed. If speed is not there, same story you want to write in the exam also means gone. Better we don't do such problems. So next problem onwards we will not write this story. Quickly we will write it within our stipulated 30 seconds or 45 seconds time. Now, in a fixed beam, he removed the entire support given numbers 1, 2. It became now like a cantilever beam, which is a statically determinate structure and immovable. You cannot move it. So, it is not necessary that we have to remove these two forces only. It is our choice. You can make it as a simply supported beam. MA, MB also we can remove and get the flexibility matrix. And accordingly, when you solve it, final results are same only, but way of solving will be different. That means you have to remove two redundants. Any two you can remove. So accordingly, your flexibility matrix will come. But such choice is not there in the stiffness matrix method. You have to fix the independent displacements only. So only one choice there. Here redundants 5 are there. Say out of 8, 5 are redundant reactions. Any 5 I can remove. So finally it should become stable, determinate, immovable structure. So let us see another way of solving the same problem. But they will give you which one you have to remove. And accordingly those things we have to remove and get the flexibility matrix. This matrix you will get by removing VB, MB. Now what is the flexibility matrix? By removing MA and MB. Now in this case we will not write entire story. You understood the process. Now find flexibility matrix with respect to coordinate system shown in figure. Now assume that they have given you the fixed beam, okay, A, B. Coordinate 1 is given to MA, coordinate 2 is given to MB. Beam given, coordinate numbers also given. Now, the released structure after removing the MA, MB, 1 is for MA, 2 is for MB. In this case, what actual problem itself they have given. Now you have to remove them and see how it looks like. The released structure after removing redundant reactions MA and MB. MA and MB is as shown in figure. In a fixed support, if you remove the fixity, it looks like hinge support. Other two reactions will be there. Here also like this, A, B. Now you got a statically, actually the axial forces are not there. So here also axial force is not there. That means HA, HB 0. So VA, VB only. So it is a statically determinate structure for vertical loading. Okay, and which is immovable. So you will get a structure like this, 1, 2. So 1 for MA, 2 for MB. Remove the moments, it becomes like a simple support, which is capable of taking horizontal and vertical forces. Horizontal, vertical forces. If vertical loading only is there, then horizontal reactions are 0. So no coordinate number need to be given. No, you don't have to release the HA, HB values. You don't have to release because no reactions also are there. So no point in removing them also. Next question we see that the horizontal coordinate 3 also we will give it and see how it looks like. Okay. That means general case. More general case is third coordinate also we can give. In this case for vertical loading only MA, MB we remove. Valid only for vertical loading. No inclined loading in this case. So HA, HB are 0. So it is determinate. Okay. Now first column. Here itself will write the first column. Because 30 seconds only time means we should not write the story. Okay. Coordinate 1, coordinate 2. What we have to do? Apply unit force at coordinate 1. 1. This one here is unit force. Okay. Because of this, how it will deflect? Like this. Okay. Now, in a simply supported beam, if you apply a moment, I told you to remember the formulas. When far end is hinged, the formula is ml by 3ei. So this is displacement at 1, but unit force also at 1. The actual formula is ml by 3ei, but m becomes 1. So you will get L by 3ei. So delta 1 1 is L by 3ei. Now this one you see, coordinate 2. How it rotated? Is it rotating clockwise or anti-clockwise? Black color line is initial position. Blue color dotted line is the final tangent. So it rotated in the anti-clockwise direction like this. But coordinate 2 is clockwise. If at all displacement and coordinate are opposite to each other, that flexibility coefficient you have to take it as negative. So now this value we have to take it as displacement at 2, because of whom? unit force at 1. This formula also we know, minus ml by 6 EI. I can write it as minus L by 6 EI. Why negative? Negative because coordinate 2 and displacement are opposite to each other. Okay, so first column over. No story, nothing, that's all is enough. This also in the exam you don't have to tell why I have taken negative, but first we should understand, so I have written. Then second column. Actual problem is this one, coordinate 1, coordinate 2. Now you have to apply, length is L say. Unit force at coordinate 2, this is 1. Unit force. Unit force is a general term. Force is a general term for load and moment. In matrix method, force means it can be representing load or moment depending on the curve that you are giving. So when you apply a moment like this, it will deflect like this. You see, it will be in the same direction. Displacement at 2. Where is the unit force? Also at 2. Now this theta b, now I have to call it as delta 22. Okay. This is nothing but say theta b, ml by 3 ei. M becomes 1. So L by 3 ei. Now this is like this. See, opposite direction. Coordinate 1 is clockwise, but displacement happened opposite. Displacement at 1. But where is the unit force? At 2. So delta 1 2 minus, when far end is hinged means half of that will be there, minus ml by 6 ei. So minus L by 6 ei. L by 3 ei. These two diagrams are required. Now we see delta flexibility matrix is equal to L by 3 ei minus L by 6 ei. This is minus L by 6 ei, L by 3 ei. If we take 3 L by 3 ei common factor, 1 minus 0.5 minus 0.5 1. Now you see we have increased the speed slightly. Next time when you are doing this, also directly write the deflection profile formulas we know. First column you find it, then check the options. If only one option matches with the first column, then directly answer it. If two options have the same first column, then you have to do the second one also. That's why ml by 3 ei, ml by 6 ei formulas you are expected to remember. Now, when you are solving such problems, like if you want to write a computer programming, let us say, then in the we have a choice of VBMB, I can take it, or MAMB, I can take it. Because of that, you see, if you take VBMB, when you release it, the flexibility matrix is different. Now flexibility matrix is different. Compatibility conditions for this case, what is the compatibility condition? Displacement delta YB is 0 and slope is also 0. YB is 0, displacement is 0, slope is 0 is the compatibility conditions. So solve them, you will get the VBMB. That's the procedure. In the second problem, what's the matrix is different? What is the compatibility conditions? Theta A 0, theta B 0. Finally 0 only, but theta A, theta B are 0. So compatibility conditions also totally different. When you are writing a computer programming, Depending on the choice of redundants, you have to write a separate program. So many programs, if you take with the VA, VBMB, then do this one. Then, if this is the VBMB, then do this. Otherwise, else, and like that, for you don't read Fortran programming, C++ and C programming when you are taking. In that, if else were there. So then, if this is that, you do this. Else, do this way. Like that, so many flexibility matrices you have to write, and so many compatibility conditions you have to solve it. So, this flexibility matrix method is not at all suitable for computer programming. But whereas stiffness matrix method, fixed quantities, dk is 5 is there, say that 5 only fixed one. So, only one stiffness matrix, only one inversion. So, flexibility matrix method is not suitable for computer programming. Okay, that we write it as the first point. Second column, this is over. We will write the note here. That conclusion, once they have asked it for a 2 marks question. The reason is what? The choice of redundants is not unique. Whatever we want, we can take it and get one flexibility matrix. Note is a 2 marks. Flexibility matrix method of analysis is not suitable for computer programming. What is the reason? Because choice of redundants is not unique. Unique means not only one way of doing the things. If they give you assertion and reasoning type, say, this is the assertion, this is the reason. Okay, we can say that assertion is and reason is correct. Reason is the correct explanation for the assertion. Okay, next. Let us see one more question. We make more general one. 1, 2, one more coordinate will give it. That means axial force is also redundant. General case, that is. Okay. Find flexibility matrix with respect to coordinate system shown in figure. Same beam we will take it. Okay, A, B. This is coordinate 1, coordinate 2. I will add coordinate 3 here. Now, that means axial force also you are asked to find. Note. First, how the released structure looks like. Released structure after removing redundants. What are the redundants? MA, MB, HB. Now horizontal thrust also will develop. HB is equal to HA. If I know HB, HA I can find. After removing the redundants MA, MB, HB is as shown in figure. Now it becomes like a hinge. Horizontal reaction also we are not removing. And here I have to write a roller. If I keep a roller, this member now it can elongate. Earlier problem it should be hinge. A, B. This is coordinate 1, coordinate 2, coordinate 3. Once you give coordinate 3, and if the displacement is for that force, if displacement is impossible, then also flexibility matrix will not exist. Here also it should be capable of displacing. So we will write the first column. See now how quickly we can make it. Coordinate 1, coordinate 2, coordinate 3. Apply unit force here. 1. It will deflect like this. When it deflects, it slightly goes in to come down this way, it has to come in. But that displacement is a second order displacement. Second order displacements we will not consider, only PL by A is the first order displacement. Then this inside movement, when you are calculating this displace, that will be a function of this displacement. That means the square term will come. So we will neglect. So that inward displacements are second order displacements. Displacement at 1, unit force at 1. This is ml by 3ei. Opposite direction. Displacement at 2, unit force at 1, minus ml by 6ei. Here inward displacement. Displacement at 3, unit force at 1, 0. We take it as all second order displacements, whether you take plastic analysis or strength of materials, wherever you take it, second order displacements are 0. So delta 310, first column. Then we will write the second column here. This point coordinate 1, coordinate 2, coordinate 3. Now you have to apply unit force here. 1. Then it will deflect like this. This is opposite to that. Displacement at 1, unit force at 2, minus ml by 6ei. This one, same direction. Displacement at 2, unit force is also at 2, ml by 3ei. Here, displacement at 3, but unit force at 2, delta 3 2, 0. Next, third column. Coordinate 1, coordinate 2, coordinate 3. Apply unit force here. 1. This one is unit force. Because of this, it will not bend. See, it is a straight line. So displacement at 1, unit force at 3, 0. No rotation. At this point, no rotation is there. Unit force at 3, 0. Here also no rotation. Displacement at 2, unit force at 3, 0. No rotation. Here, this will elongate up to here. B goes to B dash. This is displacement at 3, unit force also at 3. PL by AE means P becomes 1, L by AE. Now your flexibility matrix is like this. First column is L by 3EI minus L by 6EI 0. Here minus L by 6EI, L by 3EI 0. Here 0, 0, L by AE. But till now they didn't ask you a 3 by 3 matrix. But even if they ask you also, within our stipulated time you can complete. If they ask you coordinate 3 also is given, delta 3 3 alone they ask, say, you should be able to tell that it is L by AE. 10 seconds you should complete. Okay. So the delta 3 3 if they ask, only third one you have to take it. First draw released structure. At third coordinate apply unit force. How the deflected shape will look like? The deflected shape of the beam will tell you what should be the flexibility coefficient. Okay. So deflected shapes you should draw correctly, because when you apply force, how it deforms. I have given you many examples in the uh, deflections of trusses frames chapter. Also I have given you some deflection profiles, MDM we have given. So like that, these are simple profiles only they will ask you, because only 30 seconds time. In the test series we give you complicated deflection profiles, but that much time you will not get. That is only for practice purpose. In the exam, to increase our speed of calculations, if once you do such problems also, when you observe these things, you can solve it in within seconds time. Okay. So a 3 by 3 matrix comes like this. Now we will take continuous beams, how the flexibility coefficients are to be written. Okay. Next question. What is the value of flexibility coefficient F12? They have given you the structure like this. This point, let us say A, B, C. Not only this, they have to give the coordinate numbers 1, 2. Okay. So we have a 2 span continuous beam, span given L and L, coordinate 1, coordinate 2. That means the redundant reactions are VB. In this one direction, what redundant is there? VB. In two direction, what is redundant reaction? VC. So he is asking you to take redundant reactions as VB, VC, remove them, make it as a statically determinate immovable structure, and find F12 in 2 minutes time. Okay. So note this story you don't have to write first time, so I am writing all that. The released structure after removing redundant reactions VB and VC is like this. First you must get a released structure. Okay, this is coordinate 1, this is coordinate 2. This point say A, B, C, length is L, L. Okay. Now, if you want our solution, F12. F12 means what? Or delta 12, both mean the same. Displacement at 1 due to unit force at 2. This is what he is asking you in 2 minutes time. So, we will see how we have to manage. If you take it this one, this is the coordinate 1, coordinate 2. Apply unit force at coordinate 1. Here you have to apply 1. This one is different. This is coordinate 1, this is unit force. And find displacement here. When cantilever beam strength of material, sir told you the deflection profile, like this it will go. He is asking F1 to displacement at 1, unit force at 2. That means unit force is not here. Here, 1. Unit force. Apply unit force here. Find the displacement at this point. This is a cantilever beam displacement. We know how it deflects. Entire thing is a curve. What degree curve it is? Third degree curve. Due to point loads, you will get a. Why I am writing third degree curve is it looks like as if it is a straight line. When you are writing in your notes, you may draw as a straight line. To avoid that danger, third degree curve. We have learnt due to point loads, it is always deflection curve is third degree. Due to UDL, fourth degree. Reasons also I have given you. So, this displacement is displacement at 1 because of unit force at 2. In strength of materials, you found that this is very difficult to find. Using the strain energy Castigliano's theorem too, we have no intention of using that because of the time. So, Maxwell's reciprocal displacement theorem you have studied, reverse them, you will get same. This is also equal to, what you get here is delta 12. So, we will make it like this. Coordinate 1, coordinate 2. What we do is apply unit force here, 1. Then deflection find there. It's a third degree curve and this is straight line. This is displacement at 2 due to unit force at 1. This is third degree curve and this is straight line. That's what you have studied in SM. This is easy for us to manage. Length is L here, L here. So, delta 2, 1 is nothing but this deflection we know, WL cube by 3EI, W means 1, WL cube by 3EI plus, what is the slope here? Theta into L, WL square by 2EI is the slope into L. This is what you have learnt. WL cube by 3EI plus theta B into L. Theta B is L square by 2EI into L. So, you will get 2EI common, 3 into 2, 6. So, 5 L cube by 6 EI. This is delta 2, 1. So, delta 1, 2 or delta 2, 1. 5 L cube by 6 EI. So, one of the options is 5 L cube by 6 EI. In the exam, in 2 minutes time, our task is this first. He asked this, you found it difficult, reverse them. Put the load here, find the displacement. Same result only will get. Even that is applicable to unit moment. As Sir might have told you in the Betti's reciprocal theorem or Maxwell's reciprocal displacement theorem, two need not be forces. One can be force, one can be moment, but magnitudes must be unit. then still we can use delta 1 2 is equal to delta 2 1, as I have explained Betti's reciprocal theorem, right? So once magnitude of force, either unit force or unit moment, still we can apply reciprocal displacement theorem. Okay, so this is this one. So in 2 minutes means hardly takes 30 seconds time to find. If at all you are familiar with strength of materials formulas, if you had studied so many times, W 5WL cube by 6EI directly, if you remember, you can write it. But otherwise you have to do this way. Okay, now let us see. Now, by inspection itself, we don't want to write first column, second column and waste the time. By inspection itself, how to build the 2 by 2 matrix. This we write it as note 1. Complete flexibility matrix we are finding. Okay. Now, we have given one coefficient delta 2 1 or delta 1 2 5L cube by 6A, we got it, because only that they asked in 2 minutes time. So, we can complete say in 1 minute time. Supposing that if they ask you complete 2 by 2 matrix also, we can complete in within our stipulated time by writing only one diagram. Now you see delta 1 1 means force at 1, displacement also at 1. Other part you remove it. We know how much is the formula when load is applied, WL cube by 3EI. So W becomes 1. So delta 1 1 is L cube by 3EI. Directly we can write. Next delta 2 1 we have calculated just now, 5L cube by 6EI. Naturally this must be 5L cube by 6EI. Next delta 2 2 you see here, displacement at 2, unit force also at 2. How much is that? Delta 2 2 if I find. W L means how much? 2L. WL cube by 3EI. W becomes 1. So 8L cube by 3EI. This is what you will get. WL means 2L. WL cube by 3EI, which is nothing but 8L cube by 3EI. Like this you will get 2 by 2 matrix. You see here, compared to this L cube by 3EI, compared to delta 1 1, delta 2 2 is 8 times more. Supposing that is only for 2 spans. If you have say 6 spans, then how much high value it will be if I take like that? You will get a flexibility matrix such that one value is so small, one value is too big. Then the such type of matrices with lowest value, highest value, we call it as ill-conditioned matrix. Ill-conditioned matrix means dimensions are not at all comparable. One is so less, one is so high, then you will get errors. When you are inverting the matrices, so many errors will, a round of errors will come. Such matrices we call them as ill-conditioned matrix. In surveying, sir might have told you well-conditioned triangle, ill-conditioned triangle, right? So, ill-conditioned triangle means supposing that one dimension is 1 kilometer is there, another is only say 1 meter. Then if you are asked to form a triangle, surveying when you are taking, when you are plotting it, so many errors will come. One dimension is 1 kilometer and is 1 meter, and the round of error will be so large that you don't get accurate picture. This is ill-conditioned triangle. Well-conditioned triangles means like this it will come. If one is 3 meters, let us say, another is 4 meters, 5 meters, these values must be relatively nearby values. Then you will get a well-conditioned triangle. Possible errors are very less. So either in surveying, where you work from the From the part to the whole we should not go. And supposing that India, when you are surveying the entire Indian map, from the part to the whole if you go, then India shape, distorted shape, you will get it. From the whole to the part only you have to come, so that first all points will fix it, come to the part. That means shape will be correct. That is one concept you have studied in surveying. Second concept is well-conditioned triangles only how to make it. If ill-conditioned triangles are there, again distorted shape you will get. Similar to that here also, if you get dimensions, two different dimensions of different magnitudes, too high, too much of difference, then the matrix we call them as ill-conditioned matrix. So to get a well-conditioned matrix or ill-conditioned matrix, some precautions we have to take. Let us see what it is. This is the first point. Second point is, for two spans only you found that it is 8 times larger dimension. Note 2 will write now. Assume that we have a continuous beam like this. Okay. So big one is there, let us say. Such cases A, B, C, D, E, F. If you take the coordinates here, say 1, 2, we can take, you get a cantilever beam, 3, 4, 5. That means all the reactions you have taken as redundants. Then you will get released structure like this. So long cantilever beam you will get. This is coordinate 1, coordinate 2, coordinate 3, coordinate 4, coordinate 5. This is WL cube by 3A, where L is this one. Then this will find delta 5 you will get. You will get how much? 5L. 5L to the power 4 means 5L power 3. So many times high value you will get. The matrix you will get is ill-conditioned matrix. Okay. So, this is wrong selection of redundant forces. Wrong selection of redundant forces. Why wrong? We get, because we get ill-conditioned flexibility matrix. Ill-conditioned flexibility matrix means, as I have told you, ill-conditioned triangle, well-conditioned triangle, like that. Then what we have to do is, instead of taking the reactions, I can take MA, MB, MC, MD, ME. If I remove the moments, then what will happen? First span AB, I will choose the another set of redundants like this. Say, let us say, instead of 1, 2, 3, 4, 5, I will take blue color redundants. 1, 2, 3, 4, 5. Let us say, corresponding to this one, how I will get? If I remove the two moments here, I will get a simply supported one like this. First span, blue color one, we will take it. So, this is 1, this is 2. These coordinate numbers are given to moments. So, if this is clockwise, that means if MBA, if you take clockwise, MBC must be anti-clockwise. So, that care we have to take when you are taking this one. See here, this is clockwise, so it will be anti-clockwise. Coordinate 2. This will become coordinate 3. You see, spans are very less. ML by 3 EI, ML by 6 EI. Only 2 times more, that's all, not 125 times more as in the earlier case. 2, 3, then third one is like this. Here clockwise means here it should be anti-clockwise, coordinate 3. This is coordinate 4, and clockwise, so it will become anti-clockwise, coordinate 4. This is coordinate 5, clockwise, and here it will become anti-clockwise. Clockwise means anti-clockwise. Now you see ml by 3a, ml by 6a, only half of that, that's all. This is correct selection of redundant forces. That means MA, MB, MC, etc. MA, MB, MC, MD, ME. Because we get well conditioned flexibility matrix. Means errors will be less. Now this I remove. Okay. Now in surveying, to remember this well conditioned matrix, ill conditioned matrix, what you studied in surveying, just recollect. In surveying, sir might have told you this type of triangles. 1 kilometer, 1 meter, some other distance, let us say. This is called ill conditioned triangle. Errors will be more in plotting. Well conditioned triangles will go like this. Suppose this is say 100 meters, suppose some 200 meters like this, then accordingly some dimension will be there. This is well conditioned triangle. Errors will be less in measuring and plotting. There what errors here in when you are inverting the matrix, flexibility matrix or stiffness matrix, if dimensions difference magnitude is too high, then when you invert the matrices, errors will be getting rounded off, means errors will be magnified. That's why. Okay, now I remove this one. How to set, this is about the selection of redundants. How to select? So we should select such that each span should be separate, so that good flexibility matrix we will get. Now let us see, if at all, another way of asking is, if they give you flexibility matrix and you have to find the stiffness matrix, say. Just by inverting, you will get that matrix. See here, if delta means flexibility matrix is equal to 1 by 3 EI 1, 2, 2, 8, then stiffness matrix K is, then we will get it as like this. Stiffness matrix is inverse of flexibility matrix. Inversion we know how to take it. 1 by 3i means when you invert it, you will get 3ei by the determinant of this one, 8 into 1 minus 2 into 2. Then reverse the elements, 8, 1, this will become minus 2, minus 2. Only a 2 by 2 matrix you can invert it within say 20 seconds time. If you have a 3 by 3 matrix, say it will take lot of time, and in the exam they will not ask such questions. Okay, 8 to 2, 8. Then you will get 3 EI by 8 minus 4 means 4. 3 EI by 4, 8 minus 2, 1. One of the options will be like this. Okay. Next. Next question. (17 by 96) from the workbook. Flexibility matrix of the beam shown below is delta is equal to 1 by 3 EI 1, 2, 2, 8. If the support B settles by delta by EI units, what is the reaction at B? Now, same simple problem only they will give us. This is some beam, continuous beam, 2 span, continuous beam. Let us say A, B, C. Lengths are not known to us, but coordinates are given 1, 2. With respect to that coordinate system, they have given you the options: 0.75 delta, 3 delta, 6 delta, 24 delta. This is the problem. We have a continuous beam. This is a question, actual complete question is like this. Earlier, these are the possibilities. Either they can ask you only one coefficient, flexibility coefficient, or you can build a 2 by 2 matrix. You have to build a 2 by 2 matrix, or they will give you the matrix. You have to invert the matrix to find the unknown redundant forces. That means compatibility conditions, you have to invert it to get the redundant reactions. Let us, you have only 1 minute time in the exam. How we have to manage? What they have given, what we have to do, that we have to write it. See here, this is a question. To save our time, they removed the redundant reactions. Cantilever beam they have taken, for some length 1, 2 coordinates they have taken. They have built the flexibility matrix for us to save the time. Otherwise, we have to build our own flexibility matrix. Okay, so they have given the flexibility matrix, and they have given the displacement also. No loading is there. If loading is there, again it will take 10 minutes time to solve the problem. So final displacements they have given. Support B settling. Settling word means it goes down. So it goes downward displacement. So this at coordinate 1 delta 1, since it settles down, how much it is settling? Minus delta by EI. Because it is opposite to the coordinate 1, displacement we have to take it as negative. Negative because settlement, displacement. Displacement is opposite to coordinate 1. If he says that support B settles by delta by EI, it means that support C didn't settle at all. That means delta 2 how much? 0. Okay. So they have given the final displacements. What is this flexibility matrix? They are the displacements due to unit force. If there is unit force here and here, what are the displacements they have given? If there is VB, VC, then what are the final displacements are given? Then what is VB? If 1 biscuit 5 rupees, 3 biscuits how much? That is the question. You have 2 minutes time. Let us see what he has given in this one. First he has given delta. Let us see how to read that delta. Delta has given displacements at all coordinates. Displacements at all coordinates due to unit force. This value has given 1 by 3EI 1228. This they have given. They have also given delta. This delta, final delta. Delta is delta 1, delta 2. Two displacements they have given. What is that? First displacement is minus delta by EI. Second displacement is 0. These are what? Final displacements. Final displacements at all coordinates due to what? Due to redundant forces. That redundant forces means what? VB, VC. Due to redundant forces, we name them redundant forces PR. That means P1R, P2R. What is redundant force at one coordinate? VB. What is the redundant force at second coordinate? VC. P1R means redundant reaction at coordinate 1 is nothing but VB. Then P2R, how to read is this one, redundant reaction at coordinate 2, VC. So due to VB, VC, this is the displacement. Due to unit force, this is the displacement. Then what is P1R? That is the point. How to read this one is due to unit force, this is the displacement. Due to P redundant force, delta is the displacement. Then what is PR? So that means for one delta, for P this is this one, then PR how much? How will you get it? PR. PR is equal to delta by delta. Delta by delta. Right? So 1 biscuit 5 rupees, then 10 biscuits some 50 rupees. Then what is PR? If this is 50 rupees given, then how many biscuits? Like that. So delta by delta. This you have to write it as delta inverse delta. Earlier in the stiffness matrix method when I gave, this stiffness matrix was only one element, 1.5 Z was there. So simply P by 1.5 Z you have written. But now in the denominator it is a 2 by 2 matrix, then inverse you have to invert it, then multiply. So that's why inversion is required. So if it is only one element, no inversion required, this by that, that's all. So this is the, in 2 minutes time, this idea we should get. Okay. So PR, redundant forces, is nothing but delta inverse into delta. Delta inverse we know how to calculate, 1 by 3ei means 3ei by determinant 8 into 1 minus 2 into 2. Reverse the elements, 8, 1, minus 2 into delta. This is minus delta by ei, 0. This what we will get. So this how much is that? PR means P1R, P2R. P1R means VB, P2R means VC. You reverse 3ei by 4 into, multiply them, minus 8 delta by ei, this is 0, this is 2 delta by ei. So from this you will get VB is equal to minus 6 delta, VC is equal to 3 by 4 into 8 means 2 into 3, 6. Here 3 by 4 into 2, 6 by 4 means 1.5, 1.5 delta. Here VB minus 6 delta means VB reaction is not upward, it is downward. If any support is settling down means what? Why it will go down? Someone must pull him down. So VB will pull the support bit down. So only it's going down. So accordingly VB you got negative. Negative sign indicates that VB acts opposite to coordinate 1. So VB is downwards. Then here positive sign indicates that VC acts in the direction of 2. So VC acts upwards. It is this way, okay. So this idea we should get it. This is the core part of the problem. For one delta, for P delta, so capital delta, then P how much means delta by delta. So in the exam, in 1 minute or 1.5 minute time, we cannot do more than this one. Even if you have to do this part, they have to give us delta, because finding delta itself will take 2 minutes time or 1.5 minute time say. Then inversion, multiplication, then thinking process, our line of thinking also will be there, which takes time. So even if you take 1 minute time to think what he has given, what we have to do, another 1 minute you can complete the problem. They cannot ask more tougher questions than this one, only fundamentals. Okay. So this is how the questions will be asked in matrix methods of structural analysis, because most of the universities matrix methods is optional subject. so that they also know. That's why they ask you only on the fundamentals of matrix methods. At least some basics do you know them or not? Even in the structural dynamics also, most of the universities structural dynamics is not at all included. In the BTech level, we don't have that structural dynamics subject at all. But engineering mechanics you have studied about the uh, mechanical vibrations, time period, frequency of springs you have studied. So springs are replaced by structures. Structural stiffness you have to calculate. You can calculate because moment distribution you have studied for beams, frames, etc. We know how to calculate stiffness of a beam or stiffness of a frame. So stiffness of a spring, if you replace it by stiffness of a structure, then simple things like what is the frequency of a structure or what is the time period of a structure, up to that they can ask you without calculator in 1 minute time. That we will see the structural dynamics part now.